this lecture, we will focus on Poisson distribution. Essentially, the main distinction between Poisson distribution and binomial distribution. In Poisson distribution does not count successes and failures. Rather, it counts the number of occurrences of a particular event over a specific interval such as time or distance. Examples of Poisson distribution would be the number of cars that arrive at a toll booth over a specific period of time, number of customers who call to complain about a service problem this month, total number of home runs hit in Major League Baseball games today. So these are some examples of Poisson distribution. Again, it counts the number of occurrences of a particular event over a specific interval or in a given area of opportunity. Some of the important characteristics of Poisson distribution: the number of events under a window of time. That's what we try to figure out. The mean of Poisson distribution is shown by the Greek letter lambda. The variance of Poisson distribution is also represented by the Greek letter lambda. So the mean and variance are basically the same, and the standard deviation of Poisson distribution is root over lambda. Third important thing with regards to Poisson distribution: the number of occurrences are independent during one interval, and finally the intervals cannot overlap. So if I ask how many customers are going to show up at a bank teller in a half an hour interval, and then the next period I say how many customers are going to show up at a bank teller every 15 minutes, it's not consistent. So you have to either stick to half hour or you stick to 15 minutes. So the time interval cannot overlap. So these are a couple of things to keep in mind. Then with regards to Poisson distribution, this is what it looks like. Probability of x equals x given lambda equals e to the power negative lambda times lambda raised to the power x times x factorial, where e equal to a very standard result in math. This is the value that will always be provided, 2.71828, and x, where this is the value of lambda, expected value or mean, and x is the number of events. X can range from 0 to infinity. Now let's look at a problem and try to see how we can incorporate all the information. Suppose we have a golf. Jill likes to golf. So we like to figure out what is the probability that Jill will lose exactly 2 golf balls during her next round. So suppose Jill likes to golf. Okay, so the question will be, what is the probability that Jill will lose exactly 2 golf balls during her next round. The information that will be provided to us is lambda is equal to 4.2, that on an average x equal to 2, and we know the value of E is equal to 2.71828. Now we have to figure out probability of x equal to 2. Then we just plug in the value. So lambda is 4.2 square times 2.71828 raised to the power negative 2. I'm sorry. Negative 4.2. Okay, I guess I'm going to erase this parenthesis here. Negative 4.2. I just want to make sure I wrote the formula right. Four point two raised to the power 2 lambda to the power x, 2.71828 raised to the power negative 4.2 divided by 2 factorial. And again, keep in mind that 0 factorial is always equal to 1. Okay, that is also helpful in this kind of problem. So 4.2 raised to the power 2 is 17.64 times 2.1 divided by 2.71828 raised to the power 4.2. This would be 0.0149996 divided by 2 times 1. I think with this problem all you have to do is make sure you calculate this stuff correctly. If you have that squared away, so it's basically the manipulating the calculator. It would be 0.1323. So there's a 13.23% chance that Jill will lose exactly 2 golf balls during her next round. So that's one way of looking at it. Suppose we want to find out what is the probability that Jill is going to lose less than 2 golf balls in the second round. So this would be equal to P0 plus P1 plus Px equal to 2. Less than or equal to 2. So P, let me just erase this first one. P should be x equal to 0. So if we keep on, I think the problem with Poisson distribution, you have to make sure you are keeping the math in place. Okay. So what we can do is we can look at, first let's calculate px equal to 0. Px equal to 0 equals 4.2 raised to the power 0, 2.71828 raised to the power negative 4.2 divided by 0 factorial. Also keep in mind the 0 factorial is also equal to 1. So that's number 1. So once you solve all the problem, it's going to be 0.0150. Probability of x equal to 1. So 4.2 raised to the power 1. 2.71828 raised to the power minus 4.2. We already have the result for that, and 1 factorial is basically equal to 1. So once we do that, our result is 0.0630, and we already know what px equal to 2 is. So now we plug in all the value. Px less than equal to 2 should be equal to 0.0150 plus 0.0630 plus 0.123. We add them up, it should be 0.2103, which tells us that there is a 25% chance that Jill will lose no more than 2 golf balls during her next round. So 21.03% chance that Jill will lose no more than 2 golf balls next round. During our next round. So so these are some of the ways we can we be able to calculate some of the problems. If we try to find out what is the mean for this problem, you do not have to solve anything. Lambda equal to 4.2, variance equal to lambda is equal to 4.2, and then standard deviation equal to root over lambda equal to root over 4.2. Once we do that, 0.2 equals 2.04. So this gives you a little glimpse of how we work with Poisson distribution, and hopefully this example helps.